Let us answer this question of momentum and collision. Okay, this is a very interesting question. It says a billiard ball at rest is struck by another billiard ball of the same mass, whose speed is 6 meters per second. After an elastic collision, the striking ball goes off at an angle of 25 degrees with respect to its original direction of motion. Find the angle the struck ball makes with this direction and the final speeds of both balls. Right, so we have this scenario. All right, so let's say we have let me shade this one, the first ball, right, having mass 1, and let us also now shade the second ball here. Okay, let's call it mass 2. Now assume this the first ball goes and strikes that other ball, and remember that the speed for the first ball, okay, this one we call it initial, is equal to 6 meters per second. But the initial for the second ball is actually 0 because this one is at rest. So this one is at rest. Clear, right? So this one is 0 meters per second. Now after this one strikes this one, it's like they go separate ways but at some angles. So let's say this is the angle, this is the axis. This is the axis. Okay, so we have the blue one. Let's put the blue one here. Okay, and let's put the black one here. So assume this is their way. Okay, after they strike each other, they move like that, and the angle formed by this one, this is the angle we are saying 25 degrees. We call it theta 1. But the angle formed by this one, we don't know. It's what we need to find, the one given by 65.4. Getting the concept, right? So after collision, this one moves at its final velocity, v1f. Also, this one moves at its final velocity, v2f. But there's a problem here. The final velocity is in two components now. It is in two components. There will be this component. There will be the x component and the y component, like that. So there will be v1fx. There will also be v1fy. Same thing applies to ball number 2. So this is ball number 2. This is ball number 1. So even this one, it will be the same scenario. All right. So it will have that type of motion. Okay. So you discover that there will be v2fx and v2fy. Clear, right? So we need to take into consideration all those components. And keep in mind, what are they saying? An elastic collision. In elastic collision, both the momentum and kinetic energy are conserved. So keep that in mind. Again, another point is that they have of the same mass. We need to know angle properties that apply to objects of the same mass when they collide together. So let's proceed and see how we can handle this. So step 1 is, let's first define the variables. Okay, we define the variables. I've already given you 1i, 2i, 1f, and so forth. So I've already defined, that's the first part. Our second part, we are going to look at conservation of momentum. Remember, this is elastic collision. So let's look at conservation of momentum. Okay, so as we look at conservation of momentum, remember that momentum will be in both axes, the y and x. I think I've already defined the terms. So let's talk about the x and let's talk about what we are having in the y. All right, so let's look at the x component and let's talk about the y component. So we'll look at the x component itself, right? Let's look at the first ball. Okay, the first ball is actually having a motion in the x direction. This one is at rest, so it's neither is it moving in the x or in the y. Just just like that in the beginning, right? So the initial stage here, the initial stage, and this is just the final stage. So at the initial, remember that the conservation of momentum before and after should be the same, isn't it? So we look at the momentum. The only ball here having momentum at the initial stage is the first ball. Are you together, right? So here in the x, they're saying total momentum, all right? Total momentum, I'm talking about in the x. This one will be equal to the only ball having momentum as the initial, it is only the first one. Let's call this speed as the speed 1. And this is just the initial speed for that ball. This will be equal to, because we don't have for the second ball, which is just going to be plus 0, but we have for the final. So for the final in the x, we've got this part here, x. We also have got this part here, x. And we can say they're all going in the same direction. Hence, what we do, we are going to add them. So for the first ball, we have the mass. Remember that the mass is the same, so you don't have to say m1 and m2. I'll just trying to differentiate the two. So the mass is the same. So this mass applies to both balls. So let's go for the first ball. M1 is going like that. So, but its velocity, it's v velocity number 1, which is true, like v1 here. Now, velocity in the x. Remember, in the final is like this, right? So in the x, we always take the cosine component. So we are going to say v1 f. I'll let me put x for now. Let me just put x plus m v2 f x. I just want to simplify this part. So this part becomes v1 is equal to m v1 f. For cosine, for x we get cosine theta. Now which angle? The first angle. Plus m v2 f. F what? Cosine angle 2. We are done for the x component. Which we want, I'm going to simplify it further, okay, so that we get done with it correct. You know that we can divide mass throughout. If we divide mass throughout, we get v1 is equal to v1f cos theta 1 plus v2f cos theta 2. But we know okay, now let's go. We know what this one is, just 6. Go v1f. This angle, the first angle is 25 degrees plus v2f cos theta 2. Let's go for the y component. Okay, let's go for the y component. Now, in the y, were these balls moving in the y direction? No, that means initial momentum was eventually 0. Don't have even to think about it. We only have momentum in the y when after they bounce each other. But take note, if you look closely, the x's were going in the same direction, as you can see by the arrows. But look at in the y, one is going up and one is going down. That means the one going down is a minus, the one going up here to be a plus. Take note. So this ends up giving us m v1f. Remember, in the y we always take sine. Now we take sine if the angle is attached to the x-axis, because this is the x-axis. Then we have the y-axis here. So if the angle is attached to the x-axis and you have an x component, take cosine. If the angle is attached to the y-axis, you do the opposite, all right? So this one will go to the negative part. So m v2 f sin theta 2. Therefore, and if we evaluate everything, we divide the mass throughout, this will give us this f there sine 25 minus v2 f sine theta 2. I think from here, okay, where we are, I think we can just end there for now. Okay, let's now do everything at the same time now. Okay, start. Moving on. So we have our equation number 1 there, equation number 2. We also have to apply the issue of elastic collision, which is conservation of momentum and kinetic energy. So let's go to conservation of kinetic energy. Conservation of kinetic energy. So what are we saying? The kinetic energy before and after should be the same. So we are saying, since we've got two balls, we have the initial kinetic energy of the first ball, you square it, plus for the second one you do the same. Initial, you square, this should be equal to the final one, square, plus the same for the second ball. Don't bother about the mass, I'm just doing it for the, for the law sake. All right. Final, oh sorry, 2 here, 2 final, square, like that. But the mass is equal to, the m1 is equal to m2, we can just call it m. Clear, right? And at the same time, we know that the velocity of the second ball, initial velocity of the second ball, is just 0. That's why we had 0 momentum at the beginning. So what does this equation reduce itself to? So this becomes 1 over this, remember this just becomes m. All right, then we've got squared plus, clear. Do we have more kinetic energy here? No, we don't have, because velocity is 0, the initial. So end up only having this final squared plus half m v2 f squared. We can divide the mass throughout, and half mass and half divide throughout, we end up having v1 I squared is equal to v1 final squared plus v2 final squared. All right, but v1, remember v1 initial was 6, so squaring 6, we get 36 here. v1 f squared plus v2 f squared. So this becomes our equation number 3. We are now ready to solve the equation. Now you might be thinking of, no, I make what the circular formula, look at the angle, it will be very complicated. But there is this issue here of them having the same masses. No, it's an alternative approach if they have the same masses, all right, and one ball is initially at rest. So if they have the same masses, then one ball is initially at rest, we can consider the fact that when these two balls hit each other, they are going to move at an angle of 90 degrees perpendicular to one another. This means that the angle between them is 90 degrees. So what I mean is, we are going to assume that the angle between them is 90 degrees. This one applies when two masses, one is at rest, then the other one strikes, and there is what? They have the same mass. So assuming that fact, so we are saying theta 1 plus theta 2, this should give us 90 degrees. Theta 1 is 25 degrees plus theta 2, 90 degrees, giving us theta 2 as what? 65 degrees. Now, I know that the angle that has been given here is 65.4, which is a little bit more accurate than what we've found here. The reason is simple. To work out this problem, you can use, for example, Python. Can work out properly, but as we are going to use that concept, all right, to help us. So if that's the case, let's go to equation number 2. Okay, go back to equation number 2. Here, this one there, this one there. If I take this one the other side, this becomes, please confirm with me, v1f is equal to v2f sine 65 degrees over sine of 25 Is it true? Yes, it is. So if I take this one, the other side becomes equal to one another. I'm looking for V1F, so I have to divide it throughout. So sine 25 becomes the denominator, like that, which we can punch directly on the calculator and end up having V2F multiplied by, so 2.1445. We do the same. Let's go to equation 1. Equation 1 is just here. 6 and so forth. We can replace the angles both there. All right, we end up having 6 is equal to V1. Sorry, is it F? Okay, F. (25) plus V2F cos 65 degrees. Okay. Okay, I just want to make everything. Because we know that V1F is equal to that, so we go there. V1F here, we substitute V2F multiplied by 2.1445. Then we have cos 25 there plus V2F there cos 65 degrees. Of course, when we punch everything here, we are just getting a single number. That's a fact. Okay, so now we expand here. So if you expand here, then you add it to that one, we'll be having so we can punch cos 25 multiplied by 2.1445. Okay, then you say plus cos 65 there. So we are getting something like V2F open brackets 2.36619 and so forth. So if we divide throughout by 2.36619 and here 2.36619, V2F, I'm getting so 6 by 2.36619, I'm getting 2.5357 and so forth, which is the final velocity for the second ball. When you round this one off, you are getting 2.54 meters per second, which is what we had there. Here, the beginning, this one there, you've seen it, eh? Kwa such a velocity number 1, to be very easy, don't worry. All right, Rico, we're doing a Rico now. Recall that this was equal to that. Therefore, we said V1F is equal to V2F multiplied by 2.1445. So if we substitute here, it's 2.5. Let's write the whole of it without even rounding it. Or fine. 357 multiplied by 445. In the final 2.1445, I'm getting 5.43785 and so on meters per second. Does this also agree with what we've been given here? 5.44. You see, we can round off here so that it becomes a 4. We are there. What else do we have to find? Quasila. So we've said the angle number 2, we have said just 65, which they are giving us as 65.4, and I said you can find that one because the first technique for the angles is quite involving because you can see that there are squares and so forth. And V1 final is just 5.44. We've found that one. And V2 final we've said is 2.54, which is quite consistent. And we're done. We're done. I hope this has really helped you.